All right, so today we're going to look at more hypothesis testing. This is actually the last section in Chapter 9. You are going to need your second table, your table 8.3, the one with the degrees of freedom and the student T distribution. So if you don't have that, go ahead and maybe pause the video and dig that out because we're going to be using that today. So remember, in the last section, we looked at hypothesis testing when the standard deviation for the population was known. And so today we're going to look at the same for when we don't know the standard deviation. So the titles of these sections are really similar except for basically one word. So this is when we're not really sure what the standard deviation of the whole population is, which is actually kind of common. If you think about how large a population usually can be, it would be very challenging to do, unless you had a computer, to do the standard deviation formula for that many values, right? So when the population standard deviation is unknown, we will use the sample standard deviation instead. Remember, the sample standard deviation is uses the letter S, whereas the population standard deviation is sigma. Okay. Not surprisingly, it's not going to be as accurate. So a lot of what we're going to do today, you're going to find is not going to be quite as accurate as if it were a normal distribution, because it's not a normal distribution. It's a student T distribution, which in some ways behaves like a normal distribution, but in some ways does not. So here's where table 8.3 is going to come in. All right, we are going to need to remember that degrees of freedom is n-1. Okay, so here is how we're going to perform a hypothesis test when we don't know the standard deviation of the population. Remember, hypothesis test is where we find an H sub 0, a null hypothesis, and we find an alternate hypothesis, and then we see if we can make a conclusion from that. Remember, a whole big group of these problems aren't going to have a conclusion, so remember that. So performing a hypothesis test on a population mean when sigma is unknown. Okay. Before you begin, you do need to make sure that you have some assumptions satisfied. Okay, and here are the assumptions if you've forgotten them. N needs to be greater than 30, or maybe we have a normal population. Okay, if you already know you have a normal population, then you don't necessarily have to have N is greater than 30. The second requirement, remember, is that it's a simple random sample. So we are going to have some N's that are less than 30 in this section, but we're just going to assume that the population was normal to begin with, so we are allowed to use this process, basically. All right, so some of these steps are going to seem familiar from 9.2, but you're going to state your null and your alternate hypothesis. Remember that there are 3 choices for H sub 1, depending on whether you have a left-tailed test, right-tailed test, or a two-tailed test. Okay. Number 2, if you're going to be making a decision, by that, are you going to decide whether to reject the null hypothesis or not? You have to choose the significance level. So in other words, how confident do you want to be with your data? That's kind of what that means. Step 3 is you're going to compute the test statistic. The formula for the test statistic looks just like the one for Z, or similar. So it is mean of the sample minus mean of the population over the standard deviation divided by n, or square root of n. It's just that S is the sample standard deviation instead of the population standard deviation, and then notice instead of Z we're using T. So step number 4 is we're going to compute the p-value of the test statistic. So the p-value is going to be the area from your table under the student's t-curve with n-1 degrees of freedom. Okay. You're going to see the top row. I'm going to show you how to use it in a minute when we get to an example. You're going to look at the top row of table 8.3 to see what significance level that you're at, to know where to read on the table. And then you're going to reject H sub 0 if the p-value is less than or equal to the significance level. And then number 6 is you're going to state a conclusion. Okay, remember there's only 2 versions of the conclusion. Either you reject H sub 0 and you accept H sub 1 as the truth, okay, or you conclude that H sub 1 is true, or you don't reject H sub 0 and it's inconclusive altogether. Okay, so go ahead and have your table out and let's look at a few examples. So I want you to state an interval for P with the given conditions. All right, so let's say that I give you this information. So I gave you a t-value. Notice it's negative. We'll talk about that in a minute. I gave you an n value. It's not bigger than 30, but we're going to assume that it's a normal distribution to begin with, or that our population is a normal distribution, so we can go ahead and still proceed. And then H sub 1 says that the average is not equal to what we started with. So remember, when you have a not equal to sign, it is a two-tailed test. It is going to be important that you realize what we need to do with the two-tailed test. Okay. So here is your process for all of these. You're going to look at table 8.3 at 18 degrees of freedom. 18 because our n is 19. And what you want to do, and I'm going to show you the chart here in a minute, is you want to find the values on that row of 18 degrees of freedom that bound t. More specifically, the absolute value of t. Okay? In other words, if you look at it, all the values on this chart are positive because we're always talking about area to the right here, so t is always positive. But just know there's also a negative version of that t over here. Okay? So what I mean by that is you find 18, so I know it's a little hard to see, and you look at the row and you're looking to see values that are going to block in or bound 1.521. In other words, what's the number above it and what's the number below it. Notice these are the two numbers, right? 1.330 and 1.734. What you really care about, though, is what's up here. Okay, what are the p-values or the areas that bound those two numbers? So we're going to write down what they are. So on that row of 18 degrees of freedom, the number that was below it was 1.330, and the number that was above it was 1.734. And then if you look up at that top row, those correspond to areas of 0.10 and 0.05. Okay, so if you don't know where I got that, you need to pause the video, you need to look at your chart. We're looking at the row of 18, and we were looking to lock in this 1.521. Find the number above it, find the number below it, which were these two, okay, if we ignored the negative sign, which we have to do. And then you look up top at this row right here to figure out what the area in the tail was. Okay, so you look which numbers it is. So notice the area in the right tail, if you look at your picture on your table, is 0.10 and 0.5. But in a two-tailed test, we have two of these tails. So since this is a two-tailed test, and those areas listed on the table are only for right-tailed tests, single-tailed. So since that is true, then we have to assume that the left side looks the same as the right, and we're going to double those areas. Okay, so the answer actually is 2 times the 0.05 and then 2 times the 0.10. By the way, when you use this dual inequality format, you need to put the smallest one to the left and then the biggest one to the right. So what we end up getting is that the area is something between 0.10 and 0.20. Okay. All right, so let's look at another one. Let's say that this is our T, our N is 7, and our our alternate hypothesis looks like this. Okay, notice this is a right-tailed test because we're saying that we think the area has gotten bigger. Also notice that the T is positive. If this were just a left-tailed test, T would be negative. Because it just depends on, where on this curve it is, right? Things over here are positive, things over here are negative. So keep that in mind. All right, so what we're going to do is we're going to look at 6 degrees of freedom this time. So you're going to look at a different row. Okay, so I want you to pause the video if you can and try to figure out which areas are going to bound this T value at the row of 6 degrees of freedom. Okay. So if you pause that and figure that out, the values that bound our T value, which was 1.497. The values that are to the left and right of it are 1.440 and 1.943, which actually correspond to the same areas that we got in the previous one. The difference here is we don't need to double them because it's a one-tailed test. We only have to double them when it's a two-tailed test. All right, so the only difference, we're not going to do a left-tailed test. The only difference with a left-tailed test is the fact that T would be negative. You would ignore that negative sign and still try to bound it in at the right row. All right, so let's look at the same kind of problems, but maybe have a different value we're trying to find. So I want you to find the critical values with the given conditions. So for the first one, I want you to look at 0.05 significance level, N is 39. And we're going to say that mu is greater than what we thought. Okay, so this is a right-tailed test. Which means your t value, because that's what we're trying to find, not t, but the value from the chart would be positive, not negative, right? So it actually is a t value. So we're going to look at table A.3 at 38 degrees of freedom, that row. Okay, and instead of trying to figure out a range, we actually can just go straight for it because we know the significance level. So I'm going to move this out of the way for a minute. So we have row 38 right here. Okay, and we're going to look up at the top and scroll over until we get to 0.05. So 0.05 is 2.712. Actually, hang on. I think I read that wrong. Row 38, 0.05 I did. I went over too far. I did 0.005, so don't do what I just did there. But it looks like it's 1.686. So the critical value would be 1.686 at this level of significance. In other words, this is the value that we would say is, quote, important, okay, when we were looking at comparing values to it. Okay, so let's look at different significance level, maybe even a different row. So 0.01 is the new significance level. N is 34. And then we have something less than. So this is a left-tailed test, which should tell us that our t we're going to get is going to be negative. It's not going to read negative on the chart, but we're going to have to make it negative when we give our answer. So t will be negative because they're to the left on that curve. So you're going to look at table A.3 at 33 degrees of freedom. Okay, so again, if we look at 33 and we look at 0.01, we'll get 2.445, okay, if you look at the right row, but we know that it's going to be negative since it's left-tailed. Okay, so that's essentially how you do one-tailed tests. With two-tailed tests, you have to think a bit. And of course, we know this is a two-tailed test because, sorry, let me move that, because it says not equal to. Okay, so this is two-tailed. So with two-tailed, we have to remember that the area is actually getting split up into two pieces. This represents the outer area, and the total outer area is 0.10, which means that each of those tails is 0.05. So let's go ahead and write out our logic there. Since they're are two tails, and the area outside the significance values is 0.10, then what it means is that each tail has an area of half that, or 5%. So we're going to use that on our table, but you also need to remember that we're going to have two t's. We will actually have plus or minus t. Okay, so we're going to look at 5 degrees of freedom, right? And we're going to look at 0.05 instead of 0.10. So if you look at 5 degrees of freedom and 0.05, you get 2.015, which means that we actually have two values, one on each side, right? T is plus or minus 2.015. On Math Connect, when you want to list both, you can either usually use a comma, or they'll usually open up in your little legend box like a plus or minus button, so you can push that too, and then you can just use the plus or minus key and then enter this in. Okay, so let's go a little bit further. So this time I want you to state a conclusion if you know this to be true. N is 360. The sample mean is 25.5. The sample standard deviation is 5.3. The level of significance I want you to use is 0.01. And the question I want you to set up and answer is the mean greater than 25? Okay, so because it says is the mean greater than 25, we should know that we have a right-tailed test. Okay, so first let's set up our two hypotheses. Okay, the null hypothesis is just that the mean is going to stay 25. Okay, it's all, remember, the null hypothesis is always that the mu equals something. Okay, whereas the alternate hypothesis is where you put where your change might occur. Okay, so this is a one-tailed test, right-tailed to be exact. All right, so let's go through and figure out our test statistics. So the mean of the sample was 25.5. The mean of the population we think is 25, divided by sample standard deviation over square root of 360. And that ends up being 1.790. Okay, this is our test statistic. Okay, so we need to find a value that we can kind of compare that to. So you're going to look at table 8.3. And there is two schools of thought here. You remember back in 9.2 I taught you two different ways to do it. So I'm going to show you one way. Your Math Connect might have you go through it another way. But there's two ways to do this. Okay, so I'm going to use the p-values. So the values that bound t equals 1.79 are the following. Okay. So if you look at, by the way, there is no n equals 360, right? So you just use kind of the closest thing to it. By the way, on this chart, let's say that you had n was 49 or something, okay? You actually bump back down to 40. You don't bump it up to 50, okay, when you're trying to look for the t-value. So just kind of keep that in mind. So you're going to look at the tables, and you have p equals between these two values, right? And then what you notice, or what I hope you notice, is that the p-values in this range are not less than or equal to the significance level. Okay, in other words, these values are something in between 2.5% and 5%, which is definitely not less than 1%. So what that means is we do not reject H sub 0. And the conclusion then is that there is not enough info to make a decision, right? There's not enough info to conclude, go back to the original question, if the mean is greater than 25. Okay. All right, so I did it using the p-values. That's kind of the layout that I did, but you also could look to see if the value from the chart, how it compares specifically with 1.79, okay? So let's see, our significance level on this one was what, 0.05? So here's 0.05, and you just come down here, okay, and notice that whether we use this one or this one, right, these values are not, sorry, let me move my thing. So 0.05 takes you down here, okay, and notice that these values are not outside of our test statistic, okay. So they're not more drastically different from the mean, so we still would not reject it. So that's kind of the other way that you can use if you want to make a decision on the conclusion. Okay, so let's look at one more. And maybe we'll do this one the other way. I just kind of verbally told you how to do it the other way. But if you go back to section 9.2 again, there were two ways to look at it. You could either just compare it directly with the test statistic, or you could look at the area under the curve. So I want to kind of show you both ways. Both ways will give you the same exact conclusion. Actually, I'm going to change in to maybe be like 47, just to kind of model what you'll need to do if you find one on the homework like this. Okay, so I'm going to change that question real quick. All right, so the question asks, has the mean changed? Which means this is a two-tailed test. So we can state that we thought the mean was 3, but now we think maybe it's something different. Okay, so the first thing we can do is figure out our test statistic. So remember, that is sample mean minus population mean, and then over standard deviation divided by the square root of n. Sorry, I had to find my calculator. So that's going to look like negative 0.39. Okay, so remember when we compare that test statistic on the chart, we really just kind of consider that to be a positive. Okay. All right, so we're going to look at, so I'm going to take you through the other way. You're going to look at table A.3, okay, and the significant t-value is, so let's look at that together, okay? So remember what I said, we're going to bump in down. So we're going to look at 40. Let me scroll up. Our level of significance is 0.05, so we are going to say that our value is, oh, actually, hang on. Okay. We do need to divide our significance value by 0.05, or by 2, I mean. Okay, so I want to kind of look at this. So since it's a two-tailed test, we actually need to look at 0.05 over 2, or 2.5%. Okay, that's because it's a two-tailed test. So in other words, the area outside where we expected was 5%, so we needed to look at 0.025. So it's kind of important because it'll put us at a different value, right? So we are going to look at 40, and we're going to look at 0.025, which is 2.021. Okay, so anything bigger or outside of this range would have been, quote, unexpected. Remember, we kind of consider the absolute value here. Okay, so notice what happens is this is something different than we would have expected. So we reject H sub 0. Okay. And we conclude that the mean has changed. Okay, so this is our conclusion here. Okay, you also could have done this one where you bounded in your hypothesis values. So what I mean by that is, let me just show you this real quick. You don't have to really write this down, but this is how I actually did it before. Ignore this number, right? Hang on a minute. So I know what I messed up here. This value is actually not, I changed the numbers and I forgot that changed the answer too. So ignore what I said before. This value is not outside of this. So actually, it really changes our conclusion. I had a really, really large N before, but I wanted to do one where it wasn't so large and we had to make sure that we knew to bump it down. So sorry about that. I changed the question on the fly and forgot to change the answer. So in other words, this is the value that's significant. So anything bigger than 2.021. So think about your curve kind of like this, just so that I'm not confusing. So here's t equals 0, right? Here's 2.021. Anything outside of these two would have been unexpected, but negative 0.39 is about right here. So this is completely expected. It's in the middle. It's not in the outskirts. It's not in either of the tails. Okay. So again, in this case, we don't reject H sub 0. So there is not enough information to make a conclusion. The nice thing about Math Connect is that it's just going to have a little drop-down menu, and you're just going to have to choose, is there enough information to make a conclusion or is there not? Okay, so sorry about my error there, but that's what happens when you change problems sometimes. Okay, so last but not least, let's look at number 5. So let's say that I gave you the following values, and I want you to perform a hypothesis test on it. So is the mean greater than 2? Using the 0.05 level of significance. So rather than giving you the sample mean and the sample standard deviation, I'm just providing you with the sample, and you're going to have to find those things. So you might need to pull out your formula chart, but really on the last 2 exams, you've had to know how to find standard deviation. Just kind of a little highlight, remember that regardless of whether or not it's a normal distribution or the n is greater than 30, you shouldn't have any outliers, or a hypothesis test is not appropriate. So if there would be like a 20 or something, notice 20 would be well outside of what all these other ones are, then you actually wouldn't be able to do a hypothesis test at all. I don't think we have any outliers here though, right? They're all pretty densely packed. They're pretty close together, so no outliers, no issues there. But before we can kind of set things up, we are going to, well, I guess we could go ahead and set up a hypothesis test. Okay, so we want to know, is the mean greater than 2? Which means our hypothesis test has to look like this. The null hypothesis is that it's 2, and the alternate hypothesis is that it's something greater than 2. Okay. Notice we have 1, 2, 3, 4, 5, 6, 7, 8 values. Okay, so let's look at table 8.3 and find the critical value. Okay, so we will look at 7 degrees of freedom. Okay, let me find my chart here. 7 degrees of freedom at the 0.05 level of significance. We'll just have a one-tailed test, so we don't have to make any adjustments or anything like that. So 7 degrees of freedom at 0.05 is 1.895. So the critical value is, I forgot what I just said, 1.895. So anything outside of this, okay, will be, quote, unexpected. Or you could do the P range thing, but I think this is just as good. All right, so now we need to find T. The problem is that we don't have enough information to find T. We don't have the mean. We don't have the S. So we're going to have to find those first. Okay, so for X bar, don't overcomplicate that. That's just a mean. So you just take the sum of all, and in this case, you divide it by 8. Okay, if there are a lot of decimal places, you'll want to kind of hold on to those because this is just the middle of the problem. So notice I didn't even use a squiggly equals. This is actually exactly equal to 2.53125. So if you could carry it out to 5 or 6 decimal places and catch all of the decimals, then definitely do that. If you've forgotten, we'll find the variance first. Okay, the formula for variance, remember, is the sum of all the values minus their averages squared, and then divide that whole thing by n minus 1. Okay, I know it's been a minute, but it hasn't been that long. So here it is. First value minus average squared plus next value minus average squared plus all the way through the 8 values, and then divide that by 8 minus 1. Okay. If you do all that calculation, and you might want to pause it and see if you match up with me, but you're going to get right around 0.841698. Okay, but notice I don't want s squared, I want s, right? So to find s, you take the square root of that variance, and that works out to be about 0.917441. So I'm going to circle these, because these go in my t formula. That's why I had to find them, right? So now we can find t. So t is sample average minus population average over standard deviation divided by square root of n. Okay, so if you work all of that out, you get about 1.6378. Okay, so notice this is what we're going to compare to what we got above, right? Here was our critical value. Anything outside of that is unexpected. We did not get something outside of that. So again, I'm going to say compare 1.6378 to the critical value of 1.895, and note it is not outside of it. So don't reject h sub 0. That's our conclusion, or that's our decision, and it means there is not enough info to conclude blah blah blah. So there's not enough info to conclude that the mean is greater than 2. So I tried to show you kind of both methods there. Your homework tends to focus a little bit more on the method where you just compare t to the critical value rather than looking at a range of p's. But they still do a range of p's for certain questions, so that's kind of why I showed you both. Okay, so now you should be able to do your homework for 9.3. You also should be able to do your quiz for Chapter 9.